Hey everybody, we're going to talk about boiling point of elevation and freezing point of depression. This is the fourth lesson in topic 10. But first, let me give you a cheesy joke. There are two cannibals eating a clown. One says to the other, "Does he taste funny to you?" I don't know. I try guys. I'm trying. Alright, let's go. Okay, so first thing we're going to talk about is electrical conductivity. Conductivity is the ability to conduct an electrical current, to conduct electricity. In order to conduct electricity, you have to have positive and negatively charged particles, and they have to be free to move. If they're not free to move, you can't conduct electricity. And water itself isn't charged. It has a partially positive and a partially negative side to it, but overall it's not positive or negative. So therefore, water itself is actually a very poor conductor of electricity, contrary to popular belief. You always think about like water is a great conductor of electricity. You put electrodes in there and it shocks everybody in the water and stuff like that. And that is true for most cases because for the most part, there's things dissolved in water. Water is an excellent solvent. And so the things that are dissolved in water, the salts, they turn into ions. Salts dissolve in water and they break into their cations and their anions. And because of this, these things that are dissolved in water, that positive and negative charges that are dissolved in water, allow it to conduct electricity. And anything you add to water that allow it to conduct electricity, those things are called electrolytes. So this is a substance that when dissolved in a solvent increases the solvent's conductivity. So it's really those electrolytes that make water a very good conductor of electricity. And water always has things dissolved in it. It's kind of hard to have it not things dissolved in it. You have to distill it or deionize it. It takes a bit of work to get water to not have it in there. But water itself, not a good conductor. But water being a great solvent that it is, makes it an excellent conductor. Hope you understand that idea there. Now, at first glance, you look at this word and you go like, oh, we're going to talk about molarity again. Finally, something familiar. Look closer. It says molality. Molality, not molarity. It's kind of fun to say. Molality. Anyways, molality is a lowercase m, not a capital N. It expresses concentration in terms of moles of solute over kilograms of solvent. That's so much like molarity. Molarity is a capital M, and it's moles of solute over liters of solution instead of kilograms of solvent. So there's some very close associations with molality and molarity, and let's talk about those connections here. So molarity tells you about the moles. This is molarity again, the capital M. Molarity tells you about the moles of solute per volume of the entire solution, whereas molality tells you about the moles of solute per mass of the solvent. Keeping in mind that 1 liter of water weighs 1 kilogram, so this is the density of water. 1 liter of water weighs 1 kilogram, and sometimes in lab we're dealing with things much smaller than liters. 1 gram of water is also equal to 1 milliliter of water. So a milliliter, that's things that we might use in lab, is equal to 1 gram. That's the density of water, by the way. And that, so if 1 liter is equal to 1 kilogram, remember, molarity is moles of solute per liters of solvent, a solution. So liters of solution versus kilograms of solvent, really, what's really the only difference is solvent versus solution, because a kilogram is pretty much a liter with water. So if we keep that in mind, if we have a dilute solution, if it's dilute, that means it's a lot of water, it's a lot of solvent, very little solute. So if it's a dilute solution, the amount of solution is this, if it's a dilute solution, the amount of the solution for the solvent, you should be able to dilute, I don't know what I'm reading here. Okay, let's just start from scratch. If it's a dilute solution, your molality will equal to your molarity. So I'll read this from the beginning. Keep it in mind that 1 liter of water weighs 1 kilogram, and that for dilute solution, the amount of solution is the same as the amount of solvent. The amount of solution is the same as the amount of solvent because it's dilute. It's just mostly water. You should be able to see that dilute aqueous solutions, molality and molality are basically the same. And we're going to do some math about that later at the very, very end of this lesson. Wow, my speakers are really loud for that. It scared me. So, density. Let's talk about density here. Density is a measure of mass per unit of volume. And we talk about this when we talk about the density of water, because density of water is 1 kilogram per 1 liter. And so density can be used to describe liquids, solids, or gases. Because density relates to mass and volume, it is useful if you need to convert between molarity, which deals with volume, and molality, which deals with mass. And that connection is that for 1 kilogram, it's 1 liter. And so we use the density to kind of connect these two, molarity and molality.
I love vocabulary.
So 2 terms I need you to be comfortable with when I'm explaining about the main concepts here is the first one is dissociation. Dissociation is the energy needed to break things apart. So for stronger bonds, bond dissociation energy is higher as more energy is needed to break the bond. So dissociation is breaking things apart. And the other word is colligative properties. Colligative properties are properties that depend on the number of solute particles in a solution. So colligative properties are properties that it just matters how many things are dissolved in a solution. What the particles are, it doesn't matter. It's just how many particles are in the solution. That's colligative properties. So with using those 2 things, let's get into this. The first concept is the Van't Hoff factor. Yes, Van't Hoff. Look at that hair. I think it's interesting. To me, it looks like he's got... This is just a great picture. It looks like there's a bird coming out of his head. A little bird there. See a little bird? Anyways, the Van't Hoff factor. It's represented with a lowercase I, and it tells how many ions 1 unit of a substance will dissociate into in a solution. So, for instance, examples with the Van't Hoff factor. If we were to look at glucose, C6H12O6, this is a covalent molecule. In the last lesson, I talked to you guys about salts and how water will surround the cation and the anion and it separates them apart. And that's why salts dissolve in solution. Well, covalent bonds that are polar will dissolve in solution too, but it's really the whole molecule. The molecules separate from each other and each molecule is floating around the water and you can't see them anymore. So this is a polar covalently bonded molecule. It doesn't dissociate anymore, so its Van't Hoff factor is 1. Van't Hoff factor, by the way, is a colligative property. It's about how many pieces are going to break apart when it goes into the water. Sodium chloride, if you recall, will dissociate in water because the sodium will be, which will be as a cation, it's positively charged, will be surrounded by the oxygen side, partially negative side of water will surround that positive sodium, and the chloride will have the hydrogen side of water associating with it because it's partially positive, and the chloride will be negative. So it will break into 2 pieces, and because it breaks into 2 pieces, it has a Van't Hoff factor of 2. You need to be able to identify your ionic compounds to be able to do this lesson and to be able to understand this concept. So when you look at this, you might kind of glance at it, and hopefully when you look at this, you realize that this is a hydrogen connected to nitrate. And you recognize nitrate as a polyatomic anion. So this is hydrogen nitrate, or in solution, we call it nitric acid. And a lot of times people might think, well, the Van't Hoff factor for this would be 5. 3 oxygens, a nitrogen, and a hydrogen. Remember that polyatomic ions are covalently bonded to each other. They're not going to dissolve in the water, but the fact that nitrate it has an overall negative charge, that will be surrounded by the hydrogens of the water, and the hydrogen will be surrounded by the oxygens in the water. So this would have a colligative property of 2. You have to be able to identify those polyatomics and realize that this is a ionic compound, not a covalent compound. The next one tricks people up a little bit, so pay attention here. Calcium chloride. If you remember when we did our ionic compounds, our naming and practicing on how to do these things, we would notice that calcium chloride is CaCl2. It would take 2 chlorides to match the charge of the calcium. Calcium has a charge of +2, and so it would take 2 chlorides to match it. So when this dissociates in water, you will get a calcium and 2 chlorides. So this has a Van't Hoff factor of 3. It's going to turn into, so calcium chloride will break down into 3 different pieces. So understanding this vocabulary and these concepts here, we can talk about some good chemistry here. So when you add solute to a solution, the boiling point increases. This is called boiling point of elevation. And a lot of people, me included, put salt in their water before they boil things. They're going to make some pasta and we add some salt to the water. And a lot of people don't understand even why they're doing it. It's just kind of a tradition passed down by chefs, and a lot of us do it. Well, the chemistry behind it is as follows. When you add solute to a solution, so when you add salt to the solution, the boiling point increases. So we know that water normally would boil at 100 degrees Celsius. If we put salt in the water, it might boil at a higher temperature. It might boil at 105 degrees Celsius, 110 degrees Celsius, 120 degrees Celsius. So what good is that? Well, if you recall, if we add heat to water, we're adding energy to water, the water will increase in temperature. We want it to be hotter to cook our food. If it gets to 100 degrees Celsius, all the extra energy you're adding to the water is simply causing a phase change. It's not getting any hotter. If you turn up your stove and it's already boiling, all you're doing is making your water evaporate. It's phase changing. So the reason we put salt in water, the chemistry behind it, is it allows your water to boil at a higher temperature. So as you turn up the heat, it gets hotter. So salt in water is actually hotter than 100 degrees Celsius, which means it's hotter, you can cook your food faster, higher temperature. That's the reason why we put salt in water. There's a formula to this. The boiling point of elevation. So the boiling point of elevation, the change in temperature, so I'm talking about boiling. Normally water, say, boils at 100. So I'm going to talk about how much the water changes in temperature, that's new boiling point, is equal to the Van't Hoff factor times a constant, a boiling constant for your solvent. And for the most part, we're going to be talking about water, but this would be a constant that would be given to you if you're doing a calculation with that, times the molality. And this is why we're not using molarity. Why I even mention molality is because we're talking about molality, and that's kind of important because molality is solute, which how much salt you put in there, divided by kilograms of water. How much water do you have, and how much salt did you put in there? And this factor here, this constant, is going to be talking about kilograms of water. How much water do you actually have? So anyways, the more dilute it gets, or I'm sorry, the more concentrated you get, the more you put in there, the greater the molality, the greater the change will be. So a little bit of salt versus a lot of salt. But the Van't Hoff factor is important too. You could actually change, you can change the boiling point of water by putting sugar in there. But we learned just a moment ago that sugar has a Van't Hoff factor of 1. So we can change the molality, but this would only be 1. If we put an equal amount of salt in there as opposed to sugar, the molality would be the same, but there would be a 2 here, which would double the change in temperature. And that's why salt is a great thing to add in it as opposed to something with a Van't Hoff factor of 1. So boiling point of elevation. Adding a solute also does the same thing when we talk about freezing. When something's freezing, if you add a solute to a solution, it has to be colder than 0 degrees Celsius, because we know water normally freezes at 0 degrees Celsius. It has to get colder than 0 degrees Celsius before it can actually freeze. So This is called freezing point of depression. Freezing point of depression is when you add salt to a solution, let's say salt water, it no longer freezes at 0 degrees Celsius, it will freeze at a lower temperature. The formula for this is just like the boiling point formula, in that the change in temperature, so say 0 degrees Celsius to negative 10 degrees Celsius, whatever that change in temperature is, it's equal to the Van't Hoff factor of what is being dissolved. The more pieces it falls into, the better it is at dissolving things, times a constant, but this is not the boiling constant, this is the freezing constant for your solvent. So in most cases we'd be looking at water, times the molality. So it's the same thing, it's just talking about the constant for freezing and what you have dissolved in here. Roads generally they put salt on roads because it lowers the freezing point of depression. This makes it so to be a solid on the road, to be this ice, this sheet of ice that will be dangerous for cars and pedestrians. We put on sidewalk too. We add salt to it so that it has to be colder than 0 degrees Celsius for it to freeze. But we don't use normal salt. We don't use, or table salt I should say. We don't use sodium chloride. They use magnesium chloride. And the reason why we would use magnesium chloride is because if we recall, sodium chloride is an alkali metal and a halogen, which would dissociate into Na and Cl, would have a Van't Hoff factor of 2. But magnesium chloride is what we put on roads, because this is an alkaline earth metal, and it takes 2 chlorides to match that, to neutralize that positive charge of 2, and this is 2 negatives, and therefore when it dissociates, it turns into magnesium and 2 chlorides, so it has a Van't Hoff factor of 3. So this is important for your formula here. For the same amount of salt, the same molality, a Van't Hoff factor of 3 versus 2 is going to considerably change the temperature at which the water boils. The next thing I need to talk about is mole fractions. And mole fractions are not too hard to calculate. It is a fraction of, it's basically a ratio of the moles of solute or anything in question divided by the total number of moles of the solvent and the solute, so the whole solution. So it's represented as moles in the solution, so represented as a percentage of moles in the solution. So the mole fraction is the moles of whatever substance is questioned divided by the total moles of the solution. And I actually should state, you don't multiply this by 100. It is not a percentage, it's a fraction. So let's do a little practice with mole fractions here, if you would please. So with mole fractions, if we were to compute the mole fraction for each component in a solution of 1.25 moles of ethylene glycol and 4.00 moles of water, the first thing I want to do is take a look at the question. I have 1.25 moles of ethylene glycol and 4.00 moles of water. The question is, it's asking for 2 answers. It's asking for the mole fraction of both the ethylene glycol and the water. And when we set this up, the main thing you got to remember is that your denominator is both the solute and the solvent, or the whole solution. So to set this up for ethylene glycol, we would take the moles of ethylene glycol divided by moles of everything. So we'd add this up, 1.25 plus 4 would be 5.25. So 1.25 divided by 5.25, and you can run it in your calculators to just kind of ensure that you understand how to do this and what's going on. But when we divide this, you should get 0.238 with 3 significant figures. But the question says also, what is the mole fraction for water? So we would put water as the numerator, but still the whole solution as your denominator. And when you divide these guys out, you get 0.762 as your mole fraction. There's no units in this, all the moles cancel out. And it's important to note that if you do the mole fraction for all substances in a solution and you add them up, it will always add up to 1. So if you take these two numbers and add them up, it adds up to 1 because that's 100% of what the solution is. All right. I've got a workshop here, but before you jump into the workshop, I'm going to model number 1 for you because it's kind of more of proving a point than anything else. So I want to kind of model number 1. It is a bit confusing. You can pause the video now and try to do everything, but I suggest follow through the logic with me on number 1, both A and B, and then pause the video and answer 2, 3, 4. Okay, so let's look at number 1. Basically what I'm saying in number 1 is convert 12 molar into molality. What would be the molality of a 12 molar solution of hydrogen chloride? So to do this, let's get started. Let's try to do this here. So to do this, this is 1A. If I have a solution, I want to figure out, basically I want to figure out what 12 molar, I want to convert this into molality. What's the molality of a solution that's 12 molar? So to do this, the best thing to do is take a hypothetical amount of volume of something and convert that into how many moles of hydrogen chloride would be in it, because if you know how many moles of hydrogen chloride in it, you convert that into grams. So let me just give you a roadmap here. If we take some amount of liters, we can use molarity to figure out the moles of HCl, and then we can convert the moles of HCl into grams of HCl using the periodic table, and then we can convert that into kilograms of HCl. And you might think, what's the point of doing this right now? Well, remember that molarity equals moles per liter, but molality equals moles per kilogram. Again, this is solution, and this is just the solvent. So my goal here, is I want to figure out if I can figure out how many kilograms of hydrogen chloride are in my solution, I can figure out how many kilograms of water are in one liter. So let's walk through this here. Let's walk through this. Let's see if it makes more sense as I'm kind of doing this. So I'm just going to hypothetically start with 1 liter because I know there's 12 moles in it. I could do any volume I want, but let's do something easy here. So for every 1 liter, I know that for every 1 liter, there are 12 moles of hydrogen chloride in it. I know that because that's the molarity. So if I have 1 liter of the solution, the molarity of it is 12 moles per liter. Okay. I also know, well, the molar mass. For every 1 mole of hydrogen chloride, how many grams is that? Well, to figure that out, let's add our molar mass, which would be 1.88, and I'm adding a hydrogen and a chlorine, plus a chlorine, and chlorine is 35.453. 35.453. Add those together, and this is the molar mass of hydrogen chloride. Molar mass of hydrogen chloride is 36.461 grams of hydrogen chloride per mole of hydrogen chloride. So now I've got my grams. I need to get that to kilograms, so the last thing I should do is say there's 1,000 grams for every 1 kilogram. And what does that equal? Okay, so liters cancel with liters, moles of HCl cancel with moles of HCl, grams cancel with grams, so my answer is going to be kilograms of hydrogen chloride. And let's try that out. So that'd be 12 times 36.461 divided by 1,000. So 12 times 36.461 divided by 1,000 equals. So this is saying that I have 0.437 532 kilograms of HCl. What I just did here is I said, okay, if I have a liter, if I've got a liter of this 12 molar solution, I know by doing this, if I have a liter of this solution, I know that liter has 0.437532 kilograms of hydrogen chloride in it. Does that make sense, I hope? That if I have 1 liter, this is by mass how much hydrogen chloride in there. Okay. I also know that for water, 1 liter of water equals 1 kilogram. So if I have a liter of the solution, that's the same as having a kilogram of the solution. So our solution is, if we have 1 liter, that's the same as 1 kilogram. So if I said 1 minus 1 kilogram minus this number here, that's a constant here. So that's our whole solution. That 1 liter should be about a kilogram, and I'm going to subtract all the hydrogen chloride from it. So this is my solution, 1 kilogram. I'm going to subtract that hydrogen chloride for it. What will be left of my answer will be the kilograms of water, or my kilograms of solvent. And that is important because that's what molality is, kilograms of the solvent. So let's subtract that. 1 minus 0.437532. Is that right? 437. Yep. Looks good. Okay. And I get 0.562468 kilograms of water, which is my solvent. Okay. So that's an important number that I just solved here, this number right here, because that is my denominator for molality. Now, I can figure out my molality right now because I know, well, if 12 molar has this many kilograms of HCl in it and this much water in it, I can figure out what 12 molar solution is in molality, because I could say, okay, the molality is equal to, I've got 12 moles of HCl per, what we just solved, 12 moles of HCl per 0.562468 kilograms of solvent. And isn't that what molality is, moles per kilogram of solvent? So we have just kind of worked this into something we can use here. So let's do that. 12 divided by 0.562468 equals, and I'm going to answer this now with proper significant figures because the question was what's the molality. I got this big number here, but it's with 2 sig figs, that's 21. So the molality is 21. So to answer this question, we basically, in sum, said that 12 molar HCl is equal to 21 molality of HCl. That was basically what we solved here. That's 1A. 1B is a lot easier because we're doing the same exact thing, but we're going to substitute 1 molar instead of, 12 molar. So the second question is, what would be the molality of a 1 molar solution of HCl? So you could pause it here and try it if you want to model what we just did, but I'm going to keep going here. I'm going to kind of use what I did as a floor plan to kind of set this up quickly. So 1B, we have 1 molar into molality. And we're going to do the same thing. So I'm going to take a sample of 1 liter. And in this sample, I'm going to say that there's 1 mole instead of 12, 1 mole of HCl per liter, because that's only 1 molar, not 12 molar. But I'm going to use the same molar mass from the last one. It was 36.461 grams of HCl per mole of HCl. That was the molar mass from the periodic table. I got that number from my last question. That's when we added hydrogen and chlorine. And then I'm going to multiply that. For every 1 kilogram, there's 1,000 grams. So we're going to put all those together. And basically, that is just 36.461 divided by 1,000. You could just move the decimal place over 3 times, and you could see what that is. But let's just do it for whatever. 0.03. I'm sorry, I was actually writing the answer there. Okay, so 36.461 divided by 1,000. So that is 0.0364661 kilograms of HCl. If we subtract that from 1 kilogram, because again 1 liter equals 1 kilogram, that's the density of water. So we subtract that 1 kilogram from there, we can say 1 minus 0.036461, and we have 0.963539 kilograms of water, which is my solvent. Now we can plug that in. Now that we know the mass of our solvent, we can say, okay, now this situation, we didn't have 12 moles for every 1 mole. We have 1 mole of HCl per 0.963539 kilograms of HCl. That's what the molality equals. So 1 divided by 0.963539 equals, and with 2 significant figures, that would be 1.0 molality. All right, we did a lot of work, but let me kind of show you the point of this here. We just said that 1.0 molar equals 1.0 molality. Check that out. It equals the same thing. But when we have a concentrated situation, 12 molar, that's more concentrated, equals 21 molality. Where when it's only 1 molar, it equals 1 molality. And from the very beginning of this lesson, I told you that if it's dilute, the molarity and the molality are the same thing. Why? Because it's mostly solvent, and we just mathematically proved it. So the point of this that I need you to understand is that if it's dilute, molarity and molality are the same. And if you're doing a challenging question and it's multiple choice, you might be able to just assume the same and just quickly move through and see what answer would work. You wouldn't have to do all this conversion. And that's common that you see in AP Chem exams and stuff like that. You might see questions where that's seen if you understand the relationship of molarity to molality. And if it's dilute, it will be the same, but you might be able to rush through something and kind of assume that and see if there's a good answer. If not, you might have to do some calculations. But anyways, point being, molarity and molality are the same. Why don't you pause the video and try to answer the next few questions, and hopefully you paused it, and now you're unpausing it because I'm going to go over the answers to the next few questions. So let's try that out. Number 2, 2. What's the Van't Hoff factor for the following? Well, sodium carbonate, the Van't Hoff factor would be sodium carbonate. We identify this as it's breaking into sodium, two sodiums, because carbonate, CO3, 2 negative, is this. So because we have 3 pieces, the Van't Hoff factor for A, I'll put an A there, is 3. So Van't Hoff factor is 3 for A. B is ammonium hydroxide. Tricky question, because you have to identify, you have to realize that these are polyatomic ions here, both of them are. So it is consistent of an ammonium and a hydroxide. Actually, I put the hydroxide over here on the other one. I'll put the cation there. So this Van't Hoff factor is only 2. It's an ammonium and a hydroxide. You got to get yourself familiar with these polyatomic ions. You know, it pays off, because this always comes up, guys. You think I was kidding when I said it before? I'm not. Really important. C, we have, it looks like an iron 3 sulfate. Iron 3 sulfate. So Fe2SO4 3. So what this is going to break into is 2 irons, and 3 sulfates. Oh, this is iron 3. These are 3s, not 2s. And 3 sulfates. So what would the Van't Hoff factor for that be? It would be 5. It would be 5. There's 2 pieces here and 3 pieces there. And our final one is CCl4, carbon tetrachloride. This is not a polyatomic, and this is not an ionic compound. This is a covalently bonded compound. An easy way to tell, if you don't identify polyatomic ions here like we do here, there's no polyatomic ions here, and this is a nonmetal connected to a nonmetal. The easiest way that you can figure that out is if you see a metal connected to a nonmetal, that's ionic, but a nonmetal connected to a nonmetal, that's covalent, like sugar, and it won't dissolve in a solution. So it's just going to turn into CCl4, which has a Van't Hoff factor of only 1, and that one there tricks a lot of people, because it's you got to realize that this is covalently bonded, and water breaks things apart that are ionically charged. It's not really strong enough to break those covalent bonds, much stronger than ionic bonds. Okay, so that's number 2. Now let's use number 2. We have to use number 2 to answer number 3. Number 3 asks you, of the compounds listed in number 2, in number 2, which one would have the highest boiling point of elevation when added to water? Which would have the warmest freezing point of depression? Assume the same conditions for each. That means the same molality for everything. So really the only factor that's going to be an issue here is your Van't Hoff factor, and that's what we just figured out in number 2. So which one would have the highest boiling point of elevation? Well, the highest boiling point of elevation would be the one with the greatest Van't Hoff factor. So we have a 3, a 2, a 5, and a 1. So 5 would be the greatest. So number 3, our highest, which would be our highest boiling point of elevation, would be the iron 3 sulfate. That would be the answer to the first question. And the second question, which one have the warmest freezing point of depression? So which one dissolved in water would not really change water's freezing point very much? So that would be your lowest Van't Hoff factor, which would be this carbon chloride. So for the second part, the warmest freezing point, would be the carbon chloride. And the reason is this is a Van't Hoff factor of 5 and this is a Van't Hoff factor of 1. That's how you decide number 3. Number 4, well, let's just start another paper for number 4. Perhaps we should do that. For number 4, it says solve the mole fraction. Solve the mole fraction when we have 37 grams of ethanol is mixed with 86.6 grams of water. If you were doing that on your own, you didn't know what ethanol was, you maybe have to do a little Google search on what ethanol is, but I am here for you and I'm going to tell you what ethanol is right now. So number 4, I put ethanol on some of our prior tests and questions and like that, so you might get familiar with it. But ethanol is, I'll draw it for you. There's a hydroxyl group connected to, and there's 2 carbons. This is ethanol. So ethanol is C2, we call it 1, 2, 3, 4, 5, H5, and then we actually write an OH, or you could say H6O, but we write it like this to kind of indicate that there is 2 carbons, 5 hydrogens, and there's a hydroxyl group connected to it. There should really be a bond line there, but that's what ethanol looks like. So it's C2H5OH. So we're going to say the solution has 32.7 grams of C2H5OH, and I need to convert that into moles because it's a mole fraction. So we're going to need the molar mass of this. So for every 1 mole, there's how many grams of this. So to do this, let's do the molar mass here. 2 carbons, which would be 12.011 times 2. 2 carbons, I don't have parentheses on, oh, I do have parentheses, plus, parenthesis, we've got 6 overall hydrogens, so 6 times hydrogen is 1.008. We've got now 30.07. Now let's do that oxygen. Oxygen is 15.999. Did I not add that right? Okay. I messed that up. So 1.008 times 6 plus 2 carbons, 2 times 12.011 equals this, and then we're going to add the oxygen, 15.999. Okay, that looks better. So the molar mass of ethanol is 46.069 grams. C2H5OH. Grams of ethanol cancel with each other. So let's take that and say 32.7 divided by 46.069 equals, so we have, I'm going to put this here, 0.709805. I'll just round off that one there. Okay, and now let's do the moles of water. So water, we have 86.6 grams of water. We need the molar mass of water. So that's 1.008 times 2 hydrogens plus an oxygen, 15.999. 18.015 grams of water per 1 mole of water. So 86.6 divided by 18.015. That was kind of the hardest part of this one, in my opinion. We had to figure out our moles of ethanol and our moles of water. Now the mole fraction is just taking each one divided by the sum of both of them. Okay, so I just wrote the value of our ethanol and our water clean right next to each other so that we can kind of take a look here of what the total would be. So what is our total solution? Would be the sum of these two. So let's add these two together, and that would be 0.709805 plus 4.807105. That looks good. We add those together. And so our total solution is 5.51691 moles. And that's our total. That's our solution. So our mole fraction for ethanol, which would be C2H5OH, is equal to 0.709805 moles over the total, 5.51691 moles. So let's do that. 0.709805 divided by 5.51691. So I've got 0.12, and I'm going to answer this with 3 sig figs, so that 8's going to round up, so I'm going to put a 9 here. That's our mole fraction for the ethanol. And let's do our mole fraction for the water, and we'll be done. That would be 4.807105 moles. That's our water's moles. And our total solution again is 5.51691 moles. So let's do 4.807105 divided by 5.51691. 51691. Okay, good enough. Our mole fraction for water is 871 moles. And then the last check, if I add these two together, it should add up to 1. So 0.17129 plus 0.871 equals 1. The good sign, probably did it right. Let me know what you think, and I'll talk to you very soon.